Welcome to Short Talks from the Hill, a podcast from the University of Arkansas. My name is Harden Young, and I'm a writer here at the university. Today, I'd like to welcome Cameron Murray, an assistant professor of civil engineering. Murray's research interests include studying the performance of rapid setting and pre-stressed concrete, as well as bridge evaluation and load distribution. He recently received a $140,000 grant from the U.S. Department of Transportation to study the most effective soil cement mixtures for use in water structures. Cameron Murray, welcome to Short Talks.
Yeah, thanks for having me on the podcast.
It's great to have you. First, I guess let's just talk a little bit about rapid setting cement. What are its properties and why are they important for construction?
Yeah, so I think it's probably important to just talk about concrete first and about what regular cement is like. One thing I always impress upon my students when I teach reinforced concrete design is just how important concrete is to our modern way of life. I don't think many people think about this, but most people live in a house with a concrete foundation. They have concrete paths outside. They might park their car in a concrete driveway. They probably drive over a concrete bridge deck on the way to work. Many people work in concrete buildings. And in fact, concrete's used in the tallest buildings and the longest bridges in the world. So it's a very, very, very important material. I think the statistic I've seen is that it's the second most widely used material on Earth behind water. And we have to use water in concrete. So, we make more concrete than we make almost anything else. And concrete is a mixture of cement, rock, sand, and water. And the cement and the water react together, and that's what makes concrete, go from a plastic or liquid material to a solid. Typical concrete is made with Portland cement, and it takes somewhere around a month to gain its full strength, or roughly its full strength. So that can be limiting for things where we need strength really quickly, and that's where rapid setting cement comes in. A lot of our infrastructure problems these days require really rapid repairs. It's hard to close down bridges and stuff like that. So the material I study can go from fluid to full structural strength in around 2 hours.
Yeah, that's a significant time savings.
Yeah, and as time becomes more valuable, I think that's going to become more and more important. And another advantage of this material is Portland cement is responsible for a pretty large amount of CO2 emissions. And so environmentally speaking, there's been a lot of emphasis on improving the environmental friendliness of the concrete industry. And this rapid setting cement is a little bit easier on the environment. It requires less energy to produce. It emits less CO2. So it's a little bit better in that way as well.
So that's rapid setting cement. Can you walk us through what pre-stressed concrete is?
Yeah, so just a high level explanation of it, I guess. Concrete is very strong in compression. So, it's good for things like columns, but it's not very good in tension. So you wouldn't want to make a rope out of concrete because it's very brittle. And so generally speaking, we put steel in it in locations where the concrete would experience tension. And sort of a step forward from that would be pre-stressing the steel. So we pull on the steel, pour concrete around it. Once the concrete sets up or hardens, we can release that tension in the steel, and it puts the concrete into pre-compression or pre-stress. And so it allows us to use less material, make longer bridge spans, become more efficient. And so that's what it's most commonly used for is concrete bridges. If you live in Oklahoma or Texas, you probably see a lot of pre-stressed concrete bridges all over the place.
Okay, so that's rapid setting cement and pre-stressed concrete, but what are the ways you test this?
Well, let me think of how to answer this. So thinking about pre-stressed concrete, I don't have the numbers right off the top of my head, but a significant number of highway bridges or a significant percentage of highway bridges are made out of pre-stressed concrete. So even small improvements to the efficiency or the cost or the safety of these bridges can have a really large impact. So federal agencies and a lot of state DOTs are very interested in doing research with pre-stressed concrete. And a lot of the stuff that I study is how our theoretical methods for designing structural members with pre-stressed concrete compare to how they actually behave. So we'll build pre-stressed concrete members in the lab that are full scale, or we'll have them brought in from real projects. and we'll test them with really large hydraulic actuators. We'll apply real world loads to them and see how they behave. We kind of observe the way that they crack, how much load they can carry, how much they deform under the loads, and compare that to our design codes. And that way we can provide practitioners with a better idea of how it's going to behave in the real world, and how to make sure that it's safe and cost effective.
Okay, so that sets up my next question, which is the College of Engineering opened the Grady E. Harville Civil Engineering Research and Education Center this summer. What is the significance of this center?
We study structures in my line of work, and structures are big, and it's hard to perform testing on scaled down versions of structures. For a lot of reasons, it's just not as realistic. So if we can't test full scale structural objects, we can't really get a good idea of how they're going to perform in the real world. And so I was actually a student here. So I used our old structural engineering labs, and we were able to do a lot of good work here with those old labs, but they were just outdated. They weren't big enough. They didn't provide us enough capacity to test real world structural systems. I did my PhD in Oklahoma, and in Oklahoma, actually, the University of Oklahoma and Oklahoma State University both have structural engineering labs. So there were 2 in the state of Oklahoma, and there were 0 in Arkansas. Most big land grant schools with civil engineering programs have a structural engineering lab, and now we do too, ever since last summer 2021. And it's pretty transformational. I mean, a simple example is we have a 25-ton overhead crane now. So when you have a 25-ton crane, there's very few things you can't pick up easily, as opposed to in our old lab, the size of things we could test was limited just by the fact that we weren't able to pick very many things up.
This also has implications for industry, right? I mean, there's the research component, and then you're also talking about the testing component.
Our capabilities now allow us to do a pretty wide variety of stuff. So there's very fundamental research questions that we can do, and that may be stuff that funding agencies like the National Science Foundation are interested in. There's kind of code-based or design-based sort of questions that departments of transportation might be interested in. But yeah, like you said, there's a lot of potential for industry collaborations. So some of my work has been funded by a cement producer in California called CTS Cement Manufacturing Corporation. And they're the makers of these rapid setting cements. And if they're interested in figuring out new avenues for commercialization for these cements, they want to learn more about the properties of the cements themselves. Another industry collaboration that's already happened in the new lab, my colleague Gary Prinz has done some testing for a company that makes structural braces for buildings that are designed to be used in seismically active areas. And so that's pretty cool work that's very practical.
I mentioned a grad from the Department of Transportation in the introduction. Can you tell us a little bit about what you're doing with that?
That grant came from a US DOT center that's on our campus. It's called MARTREC. And MARTREC's goal is to do research that has to do with inland waterways. So, a lot of freight traffic and that kind of stuff is carried on waterways in the interior of the United States, like the Arkansas River and the Mississippi River. And there's a lot of physical infrastructure that goes along with that, like dams and locks and, things that control the flow of the river and allow us to transport materials on them. So the grant that we recently received from them has to do with developing very fast setting soil cement mixtures. So say there's some kind of a storm or a levee breach or something like that where there's damage to a soil structure. It's impossible to detour a river, right? There's no side rivers you can use. So if we can quickly repair those sorts of things, it can bring them up to service so that there's not a big delay and there's not costs associated with freight that isn't able to move up and down the river. And so this is actually the second grant we've gotten on this topic. The first one, we did some kind of exploratory stuff using these fast setting cements mixed with soil. And the results were fairly good. So this is a carry on from that. We're hoping to do some more in-depth testing, figure out how to optimize the mixtures so that they're cost effective and easy to apply.
So is the idea that this stuff would just, you'd create a structure and you could put it in place quickly? Or are you actually adding the cement to, to existing places that are being worn away or breached or whatever the case may be?
It could be both. I mean, what we really envision is when there's a storm and some of these structures are damaged, there can be, the disruption can be kind of instant, and the longer they take to repair, the more difficult it can be to return them to service. So say a levee is breached, if we have to wait a long time for the material to cure or set up, or we can't apply the repair technique quickly enough, it can cost a lot of money. So this could be potentially using, bringing in cement and soil and mixing it up in place to repair, a stream bank or something like that. Or it could even be using the in-place material mixed with this rapid setting cement, so that, even maybe while the storm is still going on, we can shore up the existing structure.
Okay, sounds good. I've got one final question for you. If you weren't breaking concrete for a living, what would you be doing instead?
Yeah, that's a great question. I think I can honestly say I have no idea. I've had a few mentors over the years as a student and as I progressed as an academic, and they really pushed me to try things that I didn't know about, or to pursue avenues that I wasn't aware existed. And I think if it weren't for them, I certainly don't think I would be in this position. I'm very fortunate that I get to do something that's very practical, but that has a really high impact on the world, including teaching students and passing on my knowledge to other people.
Thank you for joining us on Short Talks today.
Yeah, thanks for having me.
Music for Short Talks from the Hill was written and performed by local musician Ben Harris. For more information and additional podcasts, visit Arkansas Research. That's arkansasresearch.uark.edu, the home of science and research news at the University of Arkansas.